Okay, so thank you all for being here. We have three very interesting talks today, I think. So first of all, we have Hao Ma from Queen Mary, University of London, and then Jorge Islas from Mathematics Department, University of Liverpool. And then we have Mattia Bevilacqua from University of Liverpool Accounting and Finance Group. So first of all, can we welcome Dr. Hao Ma?
Thank you, first of all, for the kind invitation. It's actually my first time to Liverpool, and I find this city is very beautiful. Although I'm not really a football fan, but maybe at some point I can also come and join the passion. So today I'm going to present one of my projects. It's called Double Machine Learning Inference for Conditional Latent Factors. So it's a joint work with Patrick Galladini, who's from University of Lugano and Swiss Finance Institute. My name is Hao Ma, and I'm a lecturer at the School of Economics and Finance at Queen Mary, University of London. Okay? This is actually the first time I present this paper after a major update. A lot of things that we have been, changing, and so I will try to give some intuition before I come into any kind of theoretical or technical details. And if you have any questions, just ask. So the paper is about double machine learning inference conditional latent factors. So if I try to explain here, to start with, then we have conditional latent factors, which you should think as a conditional asset pricing model. Okay, so that's why it's a data analytics in finance workshop. And also, you have the keyword machine learning. So this is actually the method that we're going to use for estimation. Some of our estimators. And the inference, or the double machine learning inference, this word tells us that we are going to use the double machine learning theory to do some asymptotic inference later on. Okay, introduction. So, I hate to actually to start with some kind of an abstract formula, but if you try to think it from very high level, then what we are doing here is that we are trying to look at, our conditional asset pricing models, and we try to think of, all the interesting parameters, for example, risk premium, SEF, pricing errors, or even like some canonical correlation that is, associated with a specific asset pricing model. We can actually all write them down as kind of a formula in terms of conditional expectation, conditional variances. So the idea is that, okay, we can, because we're in a conditional kind of setup, we can write, those XT, which can be our latent risk factors or observable risk factors. We can actually ask them using any kind of machine learning method, right? So conditional mean, conditional expectation, covariances, we can use machine learning. That's why we have machine learning in this, in this project. And the conditional information will be kind of represented by some proxies like macroeconomic variables. And we also, would like to look at the smooth function, C, and then we can do some kind of inference based on that. Okay. So, I mean, it's a little bit abstract, I admit, but, to be kind of more specific, we have actually three estimators that we're going to, discuss later on. So we have conditional risk premium, we have conditional canonical correlations, and conditional pricing errors from the implied SEF. So here's what I'm going to do later on, because you're going to see maybe many equations or formulas. So just to, give you kind of a heads up, then, my target is that to represent those different things in terms of conditional means and conditional variances. And then we actually can give you a kind of theory that as long as they can be written down in such kind of format, we can actually identify, every kind of estimator that look like that. Okay. So, we start with this, example. It's called conditional risk premium of observable factors. if you know about this paper, Jiu and Xu, so it's called Asset Pricing with Omitted Factors, which is published on Journal of Political Economy, then the idea is kind of straightforward. So in the asset pricing model, if you use some factors to approximate the asset pricing model, I mean, one kind of big issue that you have will be like, okay, but suppose that I omit some factors, right? So then there will be some kind of bias. And then, what they are arguing is that the two paths from a mixed bias approach won't be robust. So in their kind of a setup, they come up with this kind of three-step procedure. So in the sense that, it doesn't matter whether you omit some factors, you miss some factors, they can actually find a latent factor space that can cover all the factors. What you only need to do when you want to, estimate those risk premium is that you project those factors, observable factors, like from a fringe, on this latent factor space, and then you can actually do the inference. So here we are doing this kind of like a conditional version, because the paper Jiu and Xu, they are doing like an unconditional version. The point is that here, this is a latent factor space that has no misspecification issue. You don't omit any kind of factors. This is actually the factors that you can observe, for example, from a fringe. You do something like this, and then this will be, the risk premium that you can get in a conditional sense. What I want to focus on or stress on is that this lambda TO, is time varying, it's kind of risk premium, and it can be written down as, combination of conditional mean, conditional variance, and conditional covariance. And later on, we're going to see, okay, so we use machine learning to estimate them, and we use double machine learning to debias the bias from the machine learning estimate. So that's why we need to use double machine learning literature. Because, I guess many of you have done, are working on machine learning, or you're very familiar with the machine learning kind of estimates. Kind of very core idea in machine learning, if you want to predict anything, is that there's it's a bias variance trade-off. Means that in order to achieve a very high out of sample accuracy, you had to sacrifice a little bit. In OLS, for example, we know that OLS estimator is unbiased estimator, so there's no such kind of a biasing here. But if you want to predict something, especially with high dimensional conditional information, and you use machine learning, like modern machine learning algorithm, then you have to actually, you inevitably, you will have some bias in your estimates. So the whole kind of idea using double machine learning is that you can actually to debias it and to make actually very reliable inference, okay? So we extract latent factors from the systematic components returns, and we have kind of a large N and large T setup. So I'm gonna maybe skip a little bit here because I want to give you the model as soon as possible. The literature, okay. So this is actually the conditional asset pricing model that we are looking at. On the left-hand side, you have YIT, right? So we have individual asset or stock I at time T. So their excess returns. Right-hand side, we have what? We have, if you forget about the first term and only look at the second term, this is a like typical factor structure, right? So if you think about from a fringe, then, or CAPM here, you have the market factor, and the coefficient in CAPM is constant. Now the difference here is that, it's time varying and it's measurable or driven by some characteristics that you can observe at previous period, okay? And to make things more challenging, this is not actually what we want, but, to make less of a problem of misspecification issue. If you know the literature, right, so like there's a famous paper also by Dacheng Xu and co-authors, it's called Taming the Factor Zoo. So Taming the Factor Zoo basically says that, okay, so if you want to use any kind of factor model to use as your asset pricing model, there's actually more than 200, and the number of factors are even growing, right? So we actually have this kind of prior that asset pricing model with factors should be a parsimonious model, meaning that you shouldn't have maybe more than 10. Most of the time it's actually 3 or 5, right? Factors in your asset pricing model. So from like over 200 factors, how can you select and but the right combination of factors to avoid the misspecification issue. Now, one way we do this is that we assume that the factors are latent factors or they are statistical factors, right? So we don't need to actually assume or manually compute those factors in the first place. We just estimate them. So now the problem becomes like, now we have the factors we don't observe, betas we don't observe, and both are time varying. So this becomes a very hard problem. The first term is nothing but to kind of normalize a little bit, right? So factors, I mean, if their conditional mean is non-zero, we can always, make this kind of a normalization. We let the factors to be the pure shock, so that have conditional mean to 0, and we take the mean out, conditional mean, to be the lambda t. So lambda t is nothing but kind of the conditional mean of the true factors, and the factors here we estimate is just normalized. Okay. So we have this conditional latent factor model, which is quite challenging to estimate, right? So we don't know anything about this. We don't know anything about this, nothing about this. So how can we identify them? That's the first task. So we had to come up with good identification strategies because factors, betas, risk premium, they are unobservable and time varying. And the first assumption we have will be this one. So to make it simplify a little bit, we assume the number of factors to be constant. Okay? But in our setup, if you refer to our paper, we can actually allow for some varying number of factors. So to make it more realistic. So here, what we do is, if you look at this, we're looking at cross-section at each time t. You assume that we're looking at individual asset. So if you look at US stock market, at every time, especially in the recent years, you have more than, for example, maybe 4 or 3 or 5,000 stocks. So this n is the number of stocks at each time t. So assume that, okay, those are the firm level characteristics, such as like firm size, market ratio, profitability, to anything that you can find, maybe by looking at CRISP or ImpUstat, data set. So what we're assuming is that simply these kind of instrument or firm level characteristics, they do not interact with error terms in the cross-sectional sense, but they interact well with the time varying risk exposure. So in other words, we're seeing that, okay, the BIT minus 1 is probably driven by those firm level characteristics, but they have nothing to do with epsilon, okay? So what can we gain from this? We just take the, portfolio return. So for example, we have firm size. We have like, we can construct actually the evaluated portfolio return, and we call them psi t. At every time t, we compute this kind of portfolio return, and essentially we can get rid of the idiosyncratic credit risk, and we can then only focus on the systematic risk and the risk premium. So that's why we have such a condition. Now, also it's quite interesting. If you look at the conditional variance of all of the portfolio returns, okay, then we can write down like this, following that formula. So it kind of means that if you want to estimate the number of factors, we just need to estimate the rank of this matrix variance of FT given the conditional information. Okay, so that in our case, this simple case, k is constant, but it can be time varying as well. So assumption 2 is that remember we have this formula now, okay, and then this psi t is something that we can estimate, and ft we still don't know them. Gamma t minus 1, we don't know them, okay? So how can we actually try to identify the ft? The target is ft here. We then use this kind of factor normalization. And pay attention is that, without loss of generality, it's just a normalization condition. So this gamma t, we can just allow them to be just, the capital K by K matrix whose columns are the standardized eigenvectors, right? So if I translate a little bit, I believe you don't need it, but then it kind of links to this PCA idea. Because in PCA, you're trying to get, the eigenvectors and then the principal components, right? The first principal component is the direction where you have the most variation, right? It is associated where you have the largest eigenvalues. So essentially, if I, then do this kind of a formula, then GT can be represented by this JT minus 1 prime and then our portfolio return. Okay. And we know that, GT is equal to FT plus lambda t, and lambda t is nothing but the conditional mean of the FT. Then we can actually have both FT vectors and their risk premium identified, right? By just using the two assumptions there. So if you look at, left-hand side, those are the parameters of interest. Right-hand side, we have psi t, which is observable. JT minus 1 is also observable up to our, normalization, right? Because JT minus 1 is from the conditional variance of the psi t here. So everything on the right-hand side, you can estimate. Same, everything on the right-hand side, you can estimate them, and you can identify both FT and lambda t in this case. Okay. So, as I said, you can think of all those as some functions of observable, inputs like psi t is something that you can construct. And conditional mean, which is just this. And this is actually a function of conditional variance, right? Because it's the eigenvectors associated with this conditional variance. So then let me repeat the parameters of interest, FT, common risks, and their risk premium can all be written down as some kind of combination or formula or functions of conditional mean and covariances and some observable, variables. Okay. So this is how we kind of extend to other kind of parameters of interest. So here, the lambda t is not the same lambda t because it has this superscript O representing observable. So what we're doing is that, okay, now we have this latent factor because then we don't need to have this misspecification issue. What we want to do is that we want to project, for example, the Fama fringe factors in this space, and then to understand the kind of unbiased or, this kind of reliable estimates of their risk premium. And without, seeing too much details, you can also see that it's just a function of conditional variances, conditional covariances, and also conditional mean. Okay. So this is what we are trying to do. And if you want to understand what kind of a factor space our latent factor space spans or not, then we can also use conditional canonical correlation. Because I don't have probably enough time, I will skip that. But bottom line is that okay, you can also write this down as just function of conditional variances, covariances, etc. So this might be more interesting to any people who are doing asset pricing or finance, right? Because for asset pricing, we know that the fundamental question could be like to estimate the SDF. So here we have actually the implied SDF from the factor model. So you can actually write this down, SDF as also a formula this way. This formula is also, again, nothing but conditional mean, conditional variance, some observable values become. So this is the gross free rate. This is actually the portfolio return we can. Okay, and the pricing error, then SDF times some test portfolios. So the test portfolio, for example, the 25 sorted portfolios, if you follow the Fama fringe approach, those are observable, and this is constructible. And then everything becomes another parameter of interest and our framework. So, so much for the identification. And now we have this kind of So we can actually, try to make a final claim for the identification strategy. So basically everything that can be written down as this formula, where you have components are like, for example, the number of factors, you can estimate them or assume them. The citing portfolio returns, you can always, and this is nothing but all kinds of conditional mean and variance. And then as long as these function phi, as we, also saw before, like the risk premium, like the risk factors themselves, and conditional pricing error, etc., they can all be written down as this formula. As long as you can write down in this formula, they're all identified with our assumptions. So this kind of gave you a very general kind of a view of how to put many things to a very large basket. As long as you can put in a lot, this basket, everything can be okay. So this is how we, use this estimation. We have the portfolio return, then we have AT. I think I need to jump a little bit. Oh, when should I stop? Sorry. Okay. Yes, and then we have the double machine learning inference to compute the standard errors. So I try to maybe skip some of that. Okay, then I can end a little bit. Okay, so now we have those identification strategies, and then, first step, we construct the portfolio returns from individual assets. Okay, then second, we estimate all those kind of conditional means, covariances, and variances. And then we have the estimates here. I will skip these for a while for the moment because this is a kind of a, the estimate of time varying number of factors, but essentially this is based on this kind of a, ratio that it will differ. I mean, the number of factors will differ depending on how much variance that you are aiming to explain in the latent factor space. So for example, when alpha is equal to 0, you're actually targeting at explaining 100% kind of R squared in the latent factor space. And then probably you need to cover as many factors that you can find. But if you want to, give yourself some kind of a, safe boundary, then alpha could be 10% or 20%, meaning that you only aim to explain like 80% of the total variation in the return space, and then that's fine. Okay. So the double machine learning inference tells us that look, if you use all those kind of estimates from the machine learning model, right? So the theta are just conditional mean, variances, covariances. By using any kind of modern machine learning, you can use lasso, random forest, or neural networks, etc. That all doesn't matter. Okay, you can use any kind of machine learning model you want to use, but the point is that all of them have bias. So how can you adjust the bias? So this is where the double machine learning literature uses kind of called Newman's orthogonality kind of idea, and they have this kind of local robust moment restriction. So the idea, if you think about the intuition, is that if you take the kind of a functional derivative at the true parameter of interest here, it should go to 0. So in this way, you can actually, use this kind of a locally kind of adjustment term so that the estimates of your, of your true parameter of interest and should be unbiased at the true functional form of your machine learning estimates. Okay. And then with that theory, we can actually derive the asymptotic normality. And this is just to, distinguish ourselves to some benchmark paper, for example, Brian Kelly, they have this instrumented principal component analysis. And there's also a new new paper on, RPCA with sieve methods. Okay? I won't go into the details for the moment, but let's jump to the empirics. So in the empirics, we use US equities from the CRISP and CompuStat, and we use the firm level characteristics from the open source asset pricing website. We have around 212 different characteristics, but because we need to make sure the N and the T both goes to infinity, meaning, in the sample size is should be large. So we select, 78, which is already very large. The YITR monthly excess returns of individual stocks and the conditional information are from the Gold and Welch paper, which they use, they just published in 2024, on RFS. We have 25 macro financial indicators to start with, because we want to also capture, longer legs and more interactions. So we include 4 monthly legs of those portfolio returns, as well as the 4 legs of the 4 legs of the indicators and 4 legs of each characteristic-based portfolio return. In total, in this conditional expectation or conditional variances, the number of predictors we use is quite large, 412. Okay. So this is the number of assets for each portfolio. So at the minimum, at each stage, we have over 500 stocks, and the portfolio with the largest number of stocks at any time is at least 2,000. So it's a little bit time varying, but at this kind of a cross-sectional limit, the result is very robust. Okay, so this is our prediction strategy. So we started with a 5-year training and 10-year validation. Every time we train and we expand our window for another month, and then we cover the whole test period. So in total, we have around 700, more than 700, 714 months. But in the outer sample, we have from 1995 until 2023. So all the results that I'm gonna show you next are purely outer sample prediction based. Thank you. So this is a number of factors. So based on what, how much variation you want to explain, you have actually different, number of factors. So the key takeaway here is that it appears that during the crisis, there are more factors and then, the non-recession period. And when we have the, risk premium, we see that actually, many of the, former fringe factors, they are counter-cyclical, like market. During crisis, the risk premium is higher versus a non-recession period. And, but, HML, RMV, RMW, they're pro-cyclical. And this momentum factor is also very largely pro-cyclical, as we can see. So this is kind of the time varying way that we have a low dimensional projection here. And if you look, right, so we have some spikes during the recession periods for market as SMB. For the momentum, it has a large negative risk premium during the financial crisis in 2008. This is also the canonical correlation, which I'm gonna skip. This might be a bit interesting. So we plot the, the factor loadings in the unspanned factor. So we are comparing actually with just pharma fringe phi plus momentum. So what I'm just plotting here is that outside of the pharma fringe plus momentum, our factor space are mostly driven by short-term reversal, then industry momentum, then operating leverage, etc. So it seems that there, every period of time, there's kind of a leading, anomaly or leading kind of a factor that is outside of the pharma fringe and momentum space. And this is a, mean absolute pricing errors. We compare with the Pharma French and IPCA. Ours are the smallest, and there are some, canonical anomalies with some standard error. So if you see, like, for example, the short-term reversal, the pricing error is still significant. But if you look at earnings to price ratio, it doesn't seem to give you any kind of abnormal return. So yeah, I mean, let me just conclude by saying that it's kind of a new and general tool for latent factor analysis in continual framework. And we established both the identification strategy as well as some normality or inference using the double machine learning literature. And our empirics think that we have a time-varying number of conditional factors, and our method delivers smaller pricing error than the benchmark model like IPCA in conditional asset pricing. And thank you.
So, are there any questions?
Yeah. So I guess you don't have enough time. I'll just ask one question. So your latent factors, do you assume a distribution for them, or how do you, I mean, how are they estimate? I mean, you estimate it through the distribution, I guess, or they estimate through an optimization algorithm. But do you have a distribution of the latent factors, or
yeah, thank you very much for the question. We don't assume any kind of specific distribution for the latent factors themselves. And regarding the estimation of them, as I kind of showed you, so they can be estimated by constructing the conditional moments through the samples, right?
Okay.
So if you are familiar with machine learning, it's also kind of embedded in machine learning. When you predict anything with machine learning, you don't need to assume kind of a distribution, something like that. So we're keeping kind of agnostic about distribution in the sense that we want to make it very model-free kind of sense to estimate the factors as well as other parameters of interest.
I see. Makes sense. Thank you.
Thank you.
Sorry, you started discussing it, but I think then you didn't have time. So intuitively speaking, what is the main difference between your method and IPCA?
Yes, thank you for the question. So first of all, if you check IPCA in the formulas of beta, I don't show it here, but okay, so maybe in equation 4. So the beta is driven in a linear way by the formula characteristics. We don't, and we want to make it as general as possible. We don't even write down any kind of formula. If you can remember, we don't have a function there. We just see that BIT has non-zero kind of a cross-sectional correlation, probably, or covariance with WIT minus 1, which is even kind of more general than equation 5. In equation 5, they're saying that, okay, there's a nonlinear function phi here, and which is driven by the formula characteristics. Does that answer your question? Yeah, thank you.
Thank you for the talk. I was interested when you were talking about ever extending time periods into the future with your test sample. How far forward are you able to look and still maintain the same level of accuracy?
Okay, so thank you. So the full test period, because it's an expanding window strategy. So every time I expand 1 month, I then predict 1 month later. So if you look at the date axis is from 1994 to up to 2023. All of them are based on the 1 month ahead prediction. Every time you you expand, then you predict 1 month, and then it covers, this like how many years? 30 years.
Okay, fine. So you only ever predict the next month.
Yes,
So-
every time I only predict next month. I don't predict like 10 years all at once.
Okay, yeah, thank you.
Thank you.
Just one extra question. The double machine learning part, that's what I didn't really get. Do you mind just explaining the concept?
I will try my best.
Oh,
What do you
you-
mean? Okay. Yes. So okay. So let me see here. So this is what we use, right? So for the double machine learning, so essentially okay. So let me try to explain maybe the challenges here, and then could be the solutions here. Challenges are that, as I said, if you use any kind of machine learning, modern machine learning methods, the estimates are biased because you're not forcing them to be unbiased estimators. It can give you actually very good performance. For example, you can allow for nonlinearity, you can have high dimensional, conditional information, but at the cost that, the estimates are always kind of biased. So that's the first challenge. The second challenge will be like, if you practice on, for example, especially neural network, right? So if you do it like in sample training, you are almost, always overfitting the model. Sorry, overfitting the data. It means that, if you think about data is a combination of signal and noise, neural network, if you give it enough number of parameters, it will always pick up not only the signal, but also the noise in the in-sample. So you also need to actually, get rid of the overfitting problem here. So this kind of idea that in double machine learning, as far as best I can understand, is that this is widely used in the causal inference. In causal inference, for instance, you have Y, which is the outcome. Then you have the partial linear regression model. You have the policy indicator, and then you want to actually estimate the policy effect, which is a coefficient in front of the policy. But then you had to also consider a lot of the control variables. The control variables back there, you can use linear, but you can also use nonlinear. Nonlinear is actually more realistic because not everything is linear. And also you may have to control for a lot of variables. So that is a nonlinear and high dimensional, which is actually the space where machine learning can work a lot. But then because machine learning estimates, they are biased, right? Then your estimate for the policy effect is also biased. So then come up with this solution that instead of the classical kind of score function, they come up with a kind of a new score function which is based on Newman orthogonality, and they prove that if you compute this, as different formula, but they also compute the functional derivative at the true parameter as well as the true function, the true function of the machine learning models. Then you see that it can give you like zero derivative, and then you can actually remove the bias. And what is more powerful is that they show that it applies to any kind of machine learning model, because somehow if you look at the convergence rate and with this kind of Newman orthogonality score function, it converges faster when you construct this score function. And this applies to even like neural networks, which has a maybe a bit slow convergence rate. And in that way, you can actually construct those kind of local robust moment restriction, do some correction, and then estimate your parameters without any bias. That's the best I can understand.
Thank you.
Thank you.
Thank you. Yes, so should we thank Hammer? Next up is Jorge Islas.
Hey. Thanks a lot for the invitation. I will talk something a bit different. So this is more like towards insurance. And a little bit the objective is to model insurance claims. So that's a little bit the context. And I would like to mention this is a joint work with Martin Blatt, who is in the University of Copenhagen, and Oscar Peralta, which is at TAM, is a university in Mexico. And a little bit what I'm going to talk about is this context of matrix distribution. So I'm going to tell you the most popular instance of matrix distribution, which is this phase type distribution. So I will tell you exactly what they are, and one particular class of multivariate phase type distributions. And then I will move to the new thing, which is this common shock phase type distribution. So it's modeling basically claims. For instance, 2 lines of business. We want to model the joint claims, 2 lines of business. And then I will go with a numerical example, one synthetic data and one with some real data. So I will start with background and a little bit of motivation of these common shocks in insurance. And is that multiple lines of business often experience correlated losses, which is for one shared exposure to some external factor, or they also call it shocks. So some examples of common shocks. A popular instance right now is natural disasters like hurricanes, earthquakes. They affect multiple lines of business. There can be also regulatory changes, so that impacts different business, or in finance, could be a recession, market crashes. So why you want to capture these common shocks? So you, for a risk management perspective, you want to accurately model this risk, and that will allow you to give some premiums, which take into account this correlation, and also for economical capital modeling, and also reserving in insurance. A little bit what we did here is just propose a new class of tractable models that can capture this initial shared influence, which is what they call the common shock, and then there might be some independent evolution of the claims. So this is based on this matrix distribution. So I'm going to tell you what's the most popular instance of matrix distributions. One naive way to think about it is that instead of having scalars in the distributions, you put matrices. So that's the most naive way to think about it. And the phase distribution is an extension of the exponential distribution, but instead of having scalars, you put matrices. I will come back in that moment to that. The formal definition is using a Markov process. So you assume that you have P transit states and 1 absorbing state of this Markov process. If you take that particular state space, so you have that the intensity matrix of this process, you can split it in this way. So you have a matrix T that gives you the movement of the process among the transit states, and you have a vector T, which gives you the intensity going to the absorbing state. And there's this relationship between small t and capital T. So you assume that the process can start in one of the transit states, so that's this part over here, but not in the absorbing state. So how this process would look like is something like this. So this is just like a type of realization. So you start in one of the transit states, and you will move around all the transit states, and eventually you will reach the absorbing state. So this P plus 1. And then we say that the time until absorption of this process is this part over here. That has a phase distribution with parameters pi, which alpha, which is the vector of initial probabilities, and this matrix T. So that's the general idea. I will show you some examples on why I told you that this is like an extension of the exponential. The exponential distribution is a particular case of a phase distribution when you take instead of matrices, you just take scalars, and that gives you exactly a phase distribution. A little bit more complicated is this generalized Erlang distribution. If you take independent random variables, which are exponential, you sum them, that it turns out to be a phase distribution. And a little bit the reason is you start in the first state, you stay there for an exponential time lambda 1, so that will be the first component. Then you move to the second state, you stay there an exponential time with parameter lambda 2, so that's the second summand, and then you move to the next state and so on. And then you sum all those times, and that will give you exactly this sum over here. There are other distributions which fall in this representation. So for instance, the hyper-exponential, which is mixture of exponentials, or what they call the Coxian distribution is also one instance of these phase types. Now, let me give you some properties on why these distributions are popular. One of them is that they have explicit expression for different functions. So for instance, this is the expression for the density and the distribution function. And all of them, they are in terms of matrices. So here we have a vector. This is what they call the matrix exponential, which can be defined as this series. And then here we have a vector. And that will give you an explicit representation of this density. You also have explicit expression for the moment. So that's the n moment of x given by this expression over here. Again, everything in terms of matrices. And the moment generating function also has an explicit expression. So that's one of the reasons these are popular. For a modeling perspective, they have this nice property. It's a dense class in the distributions on the positive real line. So that means that if you take any random variable, you can always find a sequence of these models which converge to that particular random variable. So if you have any type of data, in principle, you can find a phase type distribution which is described as that data. Now, the other property is that you can estimate these distributions. The most popular way to do it is using what they call this expectation maximization algorithm. And a little bit the reason is that this algorithm is popular in what they call the incomplete data setup, where you only observe partial information. So in this case, you only observe the absorption times, but you don't know the whole path of the Markov chain. This is just a toy example. I simulated some data, and this is an R package that I co-developed. And basically, using those 2 lines of code, I can find a distribution that fits this histogram. So for instance, that's taking dimension 1, referring to how many transit states I have. That's 1. So that corresponds to an exponential distribution. And that's how the fit will look like. If I change the dimension of the phase type, so meaning how many transit states I have, to 5, then I get something that gets closer. And I know that eventually I will find something that will resemble the histogram. So that's very straightforward. This is the univariate case. There are some multivariate families. I'm just going to talk about one that is related to the model that I'm going to present next. And is what they call this small MPH family of multivariate phase type distribution. I'm going to start with one picture which describes the idea of this construction. So you are going to have 2 Markov processes in the same state space. So we have, again, P transit states, 1 absorbing state. And the whole idea is that the 2 processes are going to start in the same initial state, which is going to be 3. And after that, they will develop independently, so they will not share anything in common except the initial state. So here is the blue path, and the gray path is the 2 Markov processes. And eventually, the gray path will get to the absorbing state, and the blue path will reach the absorbing state. And these 2, Y1 and Y2, is going to be the multivariate phase type. So this is the same idea, a little bit more general. So you have D Markov processes in the same state space, have P transit states, 1 absorbing state. So what you do is all of them, they start in the same initial point, but afterwards, they develop independent. And this is just a bit of notation. So since they started in the same state, so you only need 1 vector, which determines exactly which state they are. But afterwards, the development of each of the Markov processes is given by some different transition matrix. And as I said, then you take the absorption times of each one of the Markov processes, and then you take the vector, which is formed by those absorption times, and that is said to be multivariate phase type with parameters pi and the collection of transition matrices. The idea is relatively simple, but it turns out that this class of distributions has some nice properties. So let me give you some. So one is that you have explicit expressions for different functionals. For instance, here is the joint density, and that you obtain it quite easily. Basically, you condition on the first state, and then this is the shared element, the probability alpha k, and then you have independent development. And that's pretty much it. Even though it's quite simple, and it turns out that this is a dense class on distributions in the positive quadrant. So you have any multivariate distribution, you can always find one of these models which approximate that other model. You can also estimate this using expectation maximization algorithm. But a little bit the limitation is that it doesn't represent these scenarios where you have a single event which affects the multiple components at the same time. So that's exactly what we want to add to this type of construction, how we put explicitly this common shock, and I will come back to that now. So first, I'm going to give you again a picture which describes the main idea of how we construct this common shock phase type distribution. And everything is going to be in the biovariate case. So the idea is that you have two Markov processes, and the state space is going to be split into two parts. So we have states in E. So that's going to be a pre-shock phase, and then a set S, which is going to be the post-shock phase. The idea is that these two Markov processes will share evolution. So here, the states in E, I'm going to label it from 1 to P1. So these are representing the states on E. And the states on S is from P1 plus 1 to P. So the two processes are going to share the development here, in this part over here, in all space E. And they will jump to the other state space, S, is here. And they will then develop independently. So here you have the gray path and the blue path, and then eventually each one of the processes will get absorbed. Now, what we are going to call the common shock is precisely this time where you jump from one block to the other, is the shared part of the development. And then there's another part, which is the independent development of the two components. So you have this idea of one shared part plus two independent components. So that's the idea. So let me go a little bit more into that. As I mentioned, the core idea is that you have two processes which evolve identically in these pre-shock states. Okay? Then there's a common exit time, is tau 1, 2. And after that, they will develop independently in this post-shock state space. So we will need different parameters to establish that. So first, you need an initial state on E. So that will be determined by this alpha, is the initial distribution on the pre-shock states. You will move around the states here according to a matrix T. And then you will jump to S for the two processes. So that will give you a shock time. And then the jumps from E to S are determined by a matrix which is U. So that will determine the transition from E to S. And then these two processes will develop independently according to some Qi, Q1 and Q2. And now I'm going to put some scaling factors, and I will explain why we have these scaling factors. But the definition of this common shock phase type is basically we have the common shock, which is this tau 1, 2. And then we have scaling factors because the common shock might have a different effect on different lines of business. So it might affect in different proportion. And then we have an independent development. So you have the shared common shock plus an independent behavior. So that's the whole idea of this common shock construction. So let me now give you some properties of these distributions. So the first one is quite obvious. It turns out that the margins are univariate phase type, and the matrices which determine the behavior of the margin is given by this expression over here. Initial distribution is this one over here. It's quite easy to show that. And that means that if you want to study the marginal behavior, you can use all the tools available for univariate phase type. So that means that you can compute density, moments, other functionals, all of them are in closed form formula. And this matrix is capturing the common shock and the independent evolution through these matrices over here. Now, this is a key property to derive other properties like the joint density, and is that given the state where you enter at time tau 1, so when the jump occurs, then the residual times is tau 1 tilde and tau tilde 2. Those are conditionally independent of each other, and also the T1, 2. So that allows you to compute different probabilities. So first, for instance, this will be the probability that the common shock is equal to T and that you exist to state K. So it's given by this expression over here. So this is very similar to a phase state distribution because this tau 1, 2 is a phase state distribution. And then the residual times, so after I enter some state K, so the residual time is going to be just univariate phase time. Now, the source of dependence between this x1 and x2 comes from two places. So one is the size of the common shock, but another one is the state where you jump after the common shock. So the dependence will come for these two sources. So it's not just the size of the common shock, but also where you move after the shock. So this note that I have here, like if you look at the literature on common shock models, one popular choice is something similar here. So they have a common additive element plus some independent elements. And they usually assume that this is independent from this and independent from the other factors. So that's something different here. So the structure is completely condensing all the Markov process. And that's a key difference with respect to other popular common shock models. Now, I'm going to show you one of the functionals just because the formulas are quite messy. But basically, you can use this property over here of conditional independence. So that will give you this trivariate density. So you have the part of the common shock. Then you have the movement to this other block, the post-shock structure, and then you have some independent phase step moments. And if you integrate that formula, then you will have this quite ugly formula. But the key point here is that you can compute everything in terms of matrices. It's explicit, and they are extremely easy to compute in, for instance, in R. So there is implementation for all these matrices, and it's quite straightforward to do it. So this family also has the property that if you take any distribution on the positive quadrant and for fixed scale factors, so you take any value A1 and 2, you can always find a sequence of these common shock phase step models that converge quickly to F. So they have the same property of the MPH class, and the reason is that basically you can use the denseness of the MPH class to prove this part over here. So the important thing is that these models can capture any Watt-Berry distribution on the positive quadrant, and I will show you in a moment that they can capture dependencies which go beyond explicit common shocks. You might have or you might not have common shocks, and I will come back to that in a moment. We had something that we call the master formula. Basically, something that is very important in insurance is all these race measures. And many of these risk measures are given by this type of expression over here. So we find an explicit expression for this type of moments. And you get some explicit cases. For instance, if you want the shock time, that comes from here, just taken by certain configuration of the parameters. If you want the moment generating function, that is also a specific case here. And if you want cross moments, everything comes from here. And this formula basically allows you to compute different risk measures explicitly using matrix operations. So some of the measures that you can compute using this master formula, the Pearson correlation, entropic risk measure, value at risk. So those are classical risk measures. We also introduce some risk measures which are conditionally in the side of the shock. So you might be interested in what is the covariance between the two claim sizes, given that the common shock is above a certain level. So this is the type of conditional risk measures that we also introduce. And all of these, they have explicit expression. I will skip that, and then I will just tell you quickly about the parameter estimation. So one of the challenges is that you're in incomplete data case. So you only observe X1 and X2, but you have no idea of the size of the shock. And in general, you don't know the whole path of the Markov-Young process. And also, this is a high-dimensional space. So a common approach is to use IM. Here we derive the formulas, but we realize that this is quite complex, like the formulas are quite ugly. So we basically went for more a practical direction, which was just direct maximization of the log likelihood. And we just use some parallel computing with some C++ to make it fast, and it's quite efficient, in our opinion. I'm just going to give you a couple of examples. So one is with synthetic data. So we basically simulate 2,000 observations from a known model. So we wanted to see if we can recapture that model. And then we fitted one of these common shock pH models. So here you have some evidence of the quality of the fit. So you recover different moments perfectly. Here is just a plot of what the scatter plot and how you recover the marginal densities. And here are some of the risk measures that you can compute explicitly using the master formula. But this is the example that I want to focus more. This is real data. It's a very popular data set in insurance. It's called the Danish Fire Insurance. And here we took claim sizes, which are about 1 million Danish kroner. And we log transformed that. And I will explain in a moment why. And then we fitted one of these models. So one of the first things that we notice, here you can see that the marginals are quite well recovered, but something that we computed is just the mean values of the building and content and the size of the common shock. The common shock is quite high, so it contributes quite a big proportion with respect to the mean values. And here is an important point as well. So we plotted the distribution of the common shock, so you can explicitly compute this for the common shock. And what we observe is that it has a sharp jump at 0, about 0.6. And that represents claims which do not have a common shock. So the model can recover losses which has a common shock and losses which do not have a common shock. So that's an important finding here. And so that sharp jump is reflected in some of the risk measures. So that's why you observe this sharp jump in the different risk measures. But something that I also want to emphasize is this heavy tail stop. So this Danish fire insurance is used a lot in extreme value theory because it's known that it has heavy tails. So that's Pareto type tails. And that's the reason why we took the logarithm of the data. Because when you fit the logarithm of the data with one of these models, what you get is something which, for the real data, is something that resembles a Pareto distribution. And something that is quite important in this field of extreme value theory is how heavy is the tail. That's determined for something that is called the tail index. And the tail index, you can explicitly compute it, and it has these two values. The important message is that if you want to use extreme value theory techniques, so you usually separate the body and the tail. And for the tail, you use extreme value techniques, and you independently feed the tail, and you get indices of 2 and 1.67. And that's using extreme value theory. The important thing here is that this model over here doesn't need to split the data. It fits all the data at the same time and gives you indices which are quite close to the real thing. And you can also compute different risk measures like those ones over there. And this is just summary of what I just talked. So we construct a new model, this continuous biwave phase type distribution. So they are analytical attractable. So you have closed form expression for different functionals. You can use this master formula to compute different risk measures. And for modeling perspective, you have these denseness results that you can approximate any distribution in positive real line. So this is what I showed with the Danish data. So you don't need to have explicitly a common shock. You might have observations which do not have a common shock, and it will be captured here. And this is also coming from the Danish data that if you use one of these like log transformers, you don't need to use extreme value theory. You can just fit everything at the same time. And if you are interested in reading more about this, that's the paper, and the R code used is over there.
Thank you. Thank you, Jorge. Right, any questions?
Yeah, I was wondering, the intensities that you estimate, at the time, can this be used for time dependent lambda?
Nope. Time independent.
Okay. So you have to work more for the, okay.
Any other questions?
It's interesting to see how actuarial can relate to finance. So I have some work on systemic risk in finance. So usually what we do that, we estimate a measure of systemic risk, and then we understand that there was a common shock. In your case, your delta covar comes after you model the common shock, right?
So you don't know the common shock, and you try to capture it from the
yeah. But in your case, it's the other way around.
So the model has a common shock inside, and the fitting will find out how big that common shock is. So that's a little bit what is here. It's basically telling you might not have a common shock, and then if you have one common shock, then it might be of this side. So that's a little bit the message. Like many cases you will not have, but if you have it, it's quite big.
Thank you.
Okay, thank you. So we're going to take a 5-minute break now. The refreshments over here. We have, unfortunately, I messed up the coffee and the tea, but definitely next time we'll have the trolley. But we have water bottles and cookies. So a 5-minute break. Okay, so I won't keep you long. Just wanted to advertise some events that might be happening in the new year. We're having an AGM at 4:15. So I sent to our members the Zoom link for attending that. These are just some ideas for next year. It'll depend on speaker availability, and also we'll discuss it in the AGM, so it might change. If you have any ideas, if you'd like to be involved in an event, please send the ideas through. That would be very helpful. So either to our Merseyside email address here or to me directly. Yeah, so we'll just get through that. Reminder about the RSS International Conference. So it's in Bournemouth, September 7th to 10th, 2026. Keep in mind, our committee is still quite small. We could probably double it in size. We're allowed 12 members. So if you fancy getting involved and helping us arrange future events, please let us know. And yeah, that's it. Thank you, and see you next time.